Hey everybody. Wanted to take some time to go over the few net ionic equation problems from our homework assignment on the off chance that we don't have time to talk about them during class. So I just want to go through those three problems together right now um, and give you a detailed kind of step-by-step analysis of how everything works. So starting off with the first problem here, we have a solution of calcium chloride is mixed with a solution of magnesium sulfate. And so all we're going to do here, similar to what we've been doing in the past, is we're going to take this information and break it down. We pull out calcium chloride here, which is going to be CaCl2. And it tells us here that since this is a solution, this is going to be an aqueous compound dissolved in water. Plus our solution of magnesium sulfate, which is going to be MgSO4. And again, since this is a solution, we know that this is also going to be an aqueous compound. Now we look for our products. This is going to be a double replacement reaction, so we're looking for calcium and magnesium switching places here. Since they both have a 2+ charge, we can just simply switch these over. So we're going to have MgCl2 for magnesium chloride plus CaSO4 for calcium sulfate. Now, I left some space here at the end so that we can go and look at our solubility rules to determine if these are going to be insoluble precipitates or soluble aqueous compounds. So for magnesium chloride, we're going to go ahead, take a look at our solubility rules. For chlorides, we have all chlorides, bromides, and iodides are soluble except Ag+, Pb+, and Hg2+. So since magnesium chloride is not one of these exceptions, we know that magnesium chloride is going to be a soluble compound, and so we would write that out as aqueous then. We do the same thing for calcium sulfate. Looking for an applicable rule here, we see all sulfates are soluble except those of Ba2+, Pb2+, Ca2+, and Sr2+. So since calcium sulfate here is one of these exceptions to the rule, we know that calcium sulfate is going to be our solid precipitate in this example, and so we will have a reaction because of that. So this is just the standard double replacement reaction at this point. The next part, when we're breaking this down into the net ionic equation, is to split it up into the soluble ions for the complete ionic equation first. So we go ahead and take all of these aqueous compounds and split them apart into their individual components. So calcium chloride is going to separate into calcium, which has a 2+ charge, and is going to be an aqueous ion dissolved in the solution, plus the 2 chlorines, which are also going to be aqueous in this solution. Now notice here that I put a 2 in front of the chlorine here that didn't exist before. That's because there's the 2 over here next to the chlorines in the calcium chloride. So since we have two chlorines in calcium chloride overall, we have to make a note of that when we split this up in the complete ionic equation. So that's all I did there, is I put a 2 out in front to represent that this is 2 Cl minuses. If I put this as Cl2 minus, this is implying that you have 2 calciums that are bonded together that have an overall charge of 1 minus, and that's not the case here. We have 2 separate chlorine ions, so that's why we would put the 2 out in front to represent that each of them has a 1 minus charge and that they are their own separate entities. Okay. Same thing for magnesium sulfate here. Mg is going to have a 2+ and is aqueous, and sulfate is going to have a 2- and is also aqueous. So that's our reactant side. We do the same thing for the product side. For magnesium chloride, we have Mg 2+, which is going to be aqueous, plus 2 Cl minus, which is aqueous as well. And then our insoluble precipitate, the calcium sulfate here, is just going to stay as is. Because it doesn't dissolve into the solution, it wouldn't separate into the individual ions for the complete ionic equation. So this is just going to be CaSO4 and is going to be that solid insoluble compound. Good. Now for the net ionic equation, the only thing that we're going to do is get rid of those things called spectator ions. Now the spectator ions are the ones that don't take part in the reaction, that from beginning to end stay the same. And if things stay the same, then that means that there is no reaction that takes place for them. So for example, we see magnesium here with the 2+ charge on the left side of this equation, and a magnesium with the 2+ charge on the right side of the equation. This means that nothing has changed about this magnesium, so it doesn't actually take part in this reaction. So for the net ionic equation, I'm going to go ahead and cancel this out from one side to the other to show that this doesn't really change at all, so therefore it's not really part of the reaction. And then same thing for the Cl minuses. I have 2 Cl minus on both sides of this equation here. I can cancel both of these guys out. And again, we're just showing that the Cl minuses, because they don't change from the left side to the right side, really just don't take part in the reaction at all. Now then, we only have these few things left over here. We have the calcium with the 2+, the sulfate with the 2-, and then the CaSO4 at the end. Now, we can't cancel these out because these are currently separated terms on the left side and then together on the right side. It's similar to how in math class, if we had an equation x plus y equals xy, I couldn't just say that I want to cancel out this x over here on the left side of the equation with the x over on the right side of the equation by subtracting both sides by x. That's not really how this works. So anyway, now that I have only the parts that are going to take place in this reaction, I'm going to rewrite this out. The net ionic equation is only going to contain these parts that actually change over the course of the reaction. So I have Ca2+, which is going to be aqueous, plus SO4 2-, which will start out aqueous, is going to create calcium sulfate, which is our solid precipitate. And so that would be the complete net ionic equation for this example. Cool. Let's try out the next one then. We have number 2, solution of ammonium hydroxide is used to neutralize hydrochloric acid. So the same thing that we did before, we're just going to take what's given to us in the problem and write it out into the individual reactants. So we have ammonium hydroxide here. Ammonium is going to be NH4 with a 1+ charge, while hydroxide is going to be OH-. Since these are both the same charge, it's just going to be a 1-to-1 ratio in the compound, which is why this would be NH4 plus, whoops, no plus, NH4OH, and then hydrochloric acid is going to be HCl. It gives us this in the problem. For NH4OH, it tells us immediately that this is going to be a solution. So we know that this is going to be aqueous. For HCl, it doesn't tell us that this is going to be a solution, so we can just jump on over to our solubility rules real quick just to double check. And for the chlorides, bromides, and iodides rule, which hydrochloric acid would fall under, HCl is not going to be an exception to that rule, so that should be aqueous as well. So we have HCl, aqueous, is going to produce. This is a neutralization reaction, not that that means too much for us at this point, but as a double replacement reaction, we're looking again to switch the 2 positives, which is the NH4 and the H. And again, since NH4 and H both have 1+ charges, they are just going to switch as is. If they had different charges, we would want to double check with the crisscross rule to make sure that we're creating the correct new compounds. So on my product side, I'm going to have NH4 and Cl, which we can double check the solubility of that in a second. And then I'm going to have H combining with OH, which I'm just going to simplify as H2O. Now, already off the bat, before even checking HCl, NH4Cl, we know that H2O is a liquid. It is water, one of the most common liquids on Earth. And since this is the case, we know that this reaction is going to occur because we've created something that is not a soluble compound. But we still want to double check NH4Cl to make sure that this is going to be soluble, so we double check our rules one more time. And again, we're looking at the chlorides, bromides, and iodides rule here. We could also use the NH4 rule down at the bottom, but it's going to give us the same result. All chlorides, bromides, iodides are soluble, and NH4 is not one of those exceptions. So we know then that this is going to be aqueous as well. So same thing as before, we separate these out into their individual ions where necessary. We have NH4 is going to separate out into NH4 plus, which is aqueous, plus OH minus, which is aqueous, plus our H plus, which is aqueous, and Cl minus, which is also going to be aqueous. And on the product side, NH4 and Cl split because it's an aqueous compound in the water. So this splits again into NH4 plus Cl minus. And then our last component, forgot the aqueous signs. And then our last component is going to be this H2O, which would not split up because it is a non-soluble liquid in this example. All right, so this would be our complete ionic equation, and to get our net ionic equation, what we're going to do is double check and see which things occur on both sides of the equation. So we have NH4 plus on the left side, NH4 plus on the right side. These cancel out. We have Cl1 minus on the left side and Cl minus on the right side. Those cancel out. And then we're left with the unique options on the left side, OH minus and H plus, and H2O on the right side. So our net ionic equation then is going to be OH minus, which is aqueous, plus H plus, which is aqueous, dissolved ions in the solution, which will create H2O, which, as we saw, is going to be our liquid. And this would be the complete net ionic equation for this reaction and would allow this to occur naturally. And again, the net ionic equation here is the only parts of this that are going to matter in the reaction in the long run. Our NH4 and the Cl minus are our spectator ions. They don't actually do anything. They don't actually change from one side of the reaction to the other. The only things that are changing here are these OH minuses and H pluses coming together to create water. Good. So last problem on the review paper then. We have solutions of potassium chloride and sodium nitrate are mixed in a beaker. So same thing as we've done before. We're just going to go ahead and write out these compounds. We have KCl, which it tells us in the problem is a solution, so we know that that's aqueous, plus sodium nitrate, which is NaNO3. Again, if you're not sure about what these compounds are, always double check your crisscross rule. Always double check the crisscross rule. And again, since it said that this is a solution, we know this is going to be aqueous as well. Crisscross rule here, double checking what our new compounds are going to be. K and Na are going to switch places. Since K is a 1 plus and Na is a 1 plus, This is going to be in perfect ratio with what is already there, so we don't have to double check the Chris-Ross rule. But again, if you're not sure, always, always, always double check. So we have potassium nitrate here, KNO3, plus sodium chloride, NaCl. Now, once again, we're double checking our solubility rules to see what our soluble compound is. We have KNO3, which is going to be the nitrate rule. And we see that all nitrates are soluble. So this means that KNO3 is also going to be an aqueous compound. And NaCl, double checking again, is going to fall under the chlorides, bromides, and iodides rule here. And since it is not one of those exceptions, we know that this is also going to be an aqueous compound. So at this point, since we see that everything from the left side to the right side is aqueous, this is going to be a no reaction. And to kind of drive the point home to show why this is a no reaction, we can double check the net ionic equation to see what happens. So I'm going to split these up one more time into K plus aqueous plus Cl minus plus Na plus NO3 minus, and this is going to create K plus NO3 minus plus Na plus Cl minus. And so now to go from the complete ionic to the net ionic, what we would normally do is we would check the parts that occur on both sides. We have K plus and K plus. We have Cl minus and Cl minus, Na plus and Na plus, and NO3 minus and NO3 minus. So we realize here that for the net ionic equation, it is literally going to be nothing, because everything from the left side cancels out with something else on the right side, leaving absolutely nothing. So this really drives the point home that there is no change in these types of reactions when there is nothing but soluble compounds on both sides of the equation. So normally, if you get to this point and see the no reaction, you can just stop there and you don't have to continue. But I'm just driving the point home again by showing, and if we separate this out into the complete ionic, how everything cancels out to give us a no reaction because there is no change overall. All right. One point that I want to make that I did gloss over before, for the first two reactions here, I didn't skip over the balancing part. We notice here that if we counted everything out, there would be an equal number of everything on each side of the equation. So really this should be 1 CaCl2 plus 1 MgSO4 gives us 1 MgCl2 and 1 CaSO4. So because it's already balanced as is, I didn't go through that step. But what you would do is that you would balance this first before moving on to the complete ionic equation down here. And the reason behind that is that the balancing is going to affect the net ionic equation. Because for example, if we had something like 2 CaCl2 in our equation, when we split this up for the complete ionic, 2 CaCl2s would have 2 Cas, and 2 CaCl2s would have 2 Cl2s, which would be 4 Cl minus overall. Remember, just think about this as CaCl2 plus CaCl2, and we can see how we have 2 over here and 2 over here for 4 in total. All right. So I hope this helped, guys. Please let me know, ask questions if you have them. More than happy to go over these things again before we have our quiz on Wednesday. Awesome. Thanks for watching.